Hello again. So now we're going to go over the principle of continuity. This is a very important principle in fluid mechanics that has quite vast applications and is used very widely. So we can just jump straight into it. So the principle of conservation of mass states that mass of flow into a control volume is the same as the mass of flow out of that control volume. In other words, matter cannot be created or destroyed. It only changes from one form to another. So if we're to draw our control volume here, so we have an arbitrary control volume and we have mass of flow in this is the control volume. Principle states that the mass entering this control volume per unit time will be equals to the mass leaving per unit time plus the increase of mass in the control volume per unit time. So I'm just going to write that down because that's going to be our basic principle for this lesson. So that really is our defining principle that we will then apply to fluids and deduce the continuity equation. Suppose we have a steady flow. So what does it mean if we say that the flow is steady? So in a steady flow, the velocity of the fluid at a particular fixed point does not change in time. This is also called a stationary flow. The most important thing to note about a steady flow, we have no increase in mass within the control volume. Okay, so we've defined our steady flow. So what does that mean? If we're going to obey the principle of conservation of mass as we stated here in the beginning, but apply that to fluids, then we would have mass entering per unit time is equals to mass leaving per unit time, since after all there is no increase of mass in the control volume in a steady flow. So we can say in this case, therefore, okay, so that is our basic premise in this case for the steady flows. So we're going to try and draw a stream tube whereby we have a flow from one point to another. We're going to have a change in density, change in flow velocity, and maybe even a change in area. We don't know. This is going to be arbitrary and will allow us to make our deductions. So let's draw our stream tube there, and then we have the flow going up. Say that ends there. So on this side we will have density, we will have flow velocity, and we will have a certain area. And at point 2 we will have a certain value of density, a certain value of flow velocity, and a certain value of area. Now what the equation of continuity allows us to do is to relate these values to one another, such that even if we only had data from side 1, we could be able to deduce some information about side 2. So we'll take our equation. So let's go back to green because we're now talking about steady flow. And we know from our triangle that the mass will be equals to density times volume. So equating back the values that we had before, we can say that mass entering is equals to the mass leaving. By using our figures of density, velocity, and area, we can be able to write that in terms of mathematical formulas. So we would have so basically we are equating the mass on the left hand side to the mass on the right hand side. Now, for steady flow, the main principle of the equation of continuity is that mass entering is equals to mass leaving will be a constant. We can take this a little bit further if we then talk about incompressible fluids. So let's get another color here. Density does not change because the fluid cannot be compressed. It remains occupying the same amount of space. So density is constant. Therefore, we would have A1 is equals, therefore we would have A1 U1 is equals to A2 U2, and that will be equals to a constant which we call Q. Now this is the main formula that you need to remember for continuity. Now this formula, as I mentioned earlier, is very useful because if we have information about one side of the flow, we can be able to get more information about the second side of the flow simply by calculating what this constant is and then plugging in the different values. It has many applications, so we can go through a few of the applications. Calculating flows for pipes with changing cross sections. Also, it could be very useful for pipes emerging from a junction. We have, say, a pipe coming like this and separating into two. We know that the energy on this side will remain as the same as the energy on the other side. So we can apply continuity in this case. In the first case, we're talking about cases where we have maybe sudden contraction. So we have a decrease in area, or maybe we have a sudden expansion. So we have an increase in area. If we're able to calculate continuity, this value of Q will allow us to calculate the different values of velocity, and that way we can have a lot more information about our system. So that's pretty much it. The equation of continuity comes up again and again, a very important one, but it's very basic and you will use it a lot. Thank you for listening. Bye.